Presentation by Juan Lopez, retired from the USMC. He's going to present to us about critical infrastructure and SCADA Security 101.
All right.
Yeah, welcome, Juan.
Yeah, thank you. Okay, so I have a couple of videos. I might need to narrate because I don't have a audio cable, but we'll get the gist of what's going on. So a little about me. I spent 27 years on active duty in the Marine Corps. My specialty was network security, penetration testing before it was called that. We were just doing security audits or compliance audits back in the day. Then from there, I was able to go to the Air Force Institute of Technology to get a master's degree in information assurance, network security, and things of that nature. And I retired from the Marine Corps, and then they hired me back to be a researcher in cybersecurity at the Center for Cyberspace Research at Wright-Patterson Air Force Base in Ohio. That's the Air Force graduate school for masters and PhDs. While I was there, they was interested in what I was doing down in Camp Lejeune and some other bases when I went and did audits. Normally you do security audits, and they have a very strict schedule of when you can do things on the network so that they can attribute the defensive actions the people would take. They can attribute it specifically to what you were doing, and they can correlate it. So we spent a lot of time twiddling our fingers. And when I twiddled my fingers, I started, oh, that looks interesting. I wonder what that is. And I started jumping around the routers and switches on the base. And I started finding protocols that I've never seen before, like BACnet, DMP3, things of that nature. And I do traceroute and things like that. So, for example, a lot of what I'll do today is share with you what I've learned over the past 10, 11 years, dabbling in research and working with the private sector and some DoD agencies that have industrial control systems on their bases. And here lately, over the past 8 years or so, because of, we could say the straw that broke the camel's back was probably Stuxnet. And that was the first deliberate, cyber intrusion on industrial control system that was specifically designed to do that. There were some incidents before that, but they kind of spilled over from IT networks onto, industrial control system networks, and they got hit up a little bit. But we'll have some examples, as we go through, and I'll share with you my lessons learned about how SCADA security doesn't align very well with IT security principles if you go at it the way I did. And I've learned to reorient and how to massage securities of principles of security so they can be adapted much better for this particular area. So that's what we'll go with. A while back, when I was at the Air Force Institute of Technology before the job I have now, I was able to do a lot of applied research. And I had a lot of students who I didn't have to pay a salary to. So the Air Force requires them to do a research component to their academic degree. So I basically had free labor to do a lot. And these people are very bright. We got some of the best, brightest folks that come through there. And I use them to work on very difficult things. Like one of the things initially we didn't have good tools available to enumerate industrial control systems network. And in fact, most of the tools, device discovery tools that were available for IT networks, you come over to SCADA networks and launch them, and they would bring the systems to a screeching halt. A lot of devices, embedded devices, don't have exception handling capability. So if you throw it a malformed packet, it ran up the stack and tried to open and read and interpret it, and it would get stuck. And it would stay there till somebody figure out that something was wrong with the process, and then they would either outright replace the device because they didn't know how to troubleshoot it, or the system integrator 1-800 number response time was 3 days because they were from another state, or they just want to hide it under the rug that something went bad on their watch, and they just reboot the system. All right, so those are some of the things that were happening. I'll show you a video here of an interview we did because some folks got really interested in what we were doing. I'll try to put the microphone so you can hear it. And what I did on this video, we show some research we did where I had a live demos. I had a lot of senior leaders come through, and they wanted to understand what hacking SCADA would look like. So, you know, I have my peoples there, and they would run code, you know, hacking on the keyboard. You got the stuff just flying across the screen, and they're like, I don't get it. Right? So they needed something more visual. So we came up with this demo to show them. So I'll play this for you now, and I'll just be quiet for a second so you kind of figure out what's going on. But I will precursor this is what you're seeing is an actual exploit on a programmable logic controller, which I believe is the Achilles heel for most industrial control systems. And you'll have two screens. So the one screen on the right that you're seeing up there right now is a HMI interface over a PC. This is what the control operator would normally see and monitor. And then the one on the left is a bad guy screen, so you can see what they're doing, and you see the effects side by side.
The computers controlling your local power plant are simple machines, designed to perform the most basic tasks in the last 15 to 20 years. But it's their simplicity that makes them vulnerable to hackers. As internet-connected billing and the smart grid have become more prevalent, these computers, developed before viruses and hacking were common, have become accessible to the outside world and to hackers.
Now, a simple cyber attack could make it appear as though there might be a rolling blackout or physically actually cause real damage.
Juan Lopez leads a team at the Air Force's Center for Cyberspace Research in Ohio. They've built a simulator showing just how easy it is to manipulate the computers inside a power plant. In a matter of seconds, Lopez can enter the system, inject commands into the computers, and exit before anyone knows he was there.
Okay, so here we've interrupted the communication. The black lines are the bad traffic. If you look over, the control operator is not able to control anything at this moment. And after a short delay, you will see errors start to appear on the screen, which indicate that the system has lost communication and control.
The Air Force's stated mission is to fly, fight, and win. In air, space, and cyberspace.
So I'll stop that right there. It's because the interview keeps going, and then they show another technology that we kind of developed to prevent some exploits on programmable logic controllers. But basically, this is very easy to do. I targeted, and Alan Bradley. Anybody know what a PLC is by any chance, right? So some of you in here. I used to do a brief like this about 5 years ago. I might get 5 people in the room. It looks like we got about 25, so the interest is getting much bigger. But it's very easy to do that type of exploit. And it's not really an exploit because when I first started doing this, it was all about trial and error, and just about anything you did worked. And I just sit around going, oh, field goal, you know, that worked. I had some kind of effect. So let's take a walk back so that what I start presenting later on, you'll have a better understanding of why we are having all these issues with securing this space. So industrial control systems basically follow 3 generations. So I kind of borrowed another gentleman's concept of defining this by generations. So first generation SCADA systems from about the 1960s to the 80s. These were mainframe systems. They use a lot of serial line communications and the most of the components at the endpoint. And you're going to hear me coming back to that because right now the issue is that we can't secure the endpoint. And how is that different than endpoints on IT networks? And I'll get to that a little bit later on. But they made heavy use of telephone modems, and that's why they stay hidden from cybersecurity for so long. But now we're seeing that wireless connectivity is overtaking the telephone dial-up connections for remote connectivity, and of course that makes them more seeable to the attacker community. And most of what these people do here, the asset owners, are because of cost effectiveness. all right, reducing their operating costs, being more efficient. So I started to try and figure out why were they going wireless instead of telephone modems. And for remote connectivity, reason being is this. Here's an example. One CEO says, well, you know what? That phone line, we went back and looked at how much is actually used for remote connectivity. And since these systems operate in an automatic manner for long periods of time with very little human interaction, the amount of dial-up, how many days in the year added up to just over 30 days. So they were paying a recurring cost every month to have that line available. And every couple of years, the cost of that leased line from the telephone company went up. Not to say, not to exclude the fact that it seems sometimes like you pay half of your phone bill is more taxes than it is actually using the phone. So I said, for the price of one monthly bill I pay for a phone line, I can go out and buy a wireless router. And I've saved money for the rest of the year. And oh, by the way, I saved the money of taking my company employee away to go meet the troubleshooting guy, take the company vehicle, drive all the way out to the site, let them in the gate, in the building to go terminal into the box to figure out what's wrong, and then maybe have to go back out again later if a part needs to be replaced. So now they save all that money, right? Now they can have the company system integrator troubleshooter just show up, or even worse shit like they do now. Their maintenance contracts, when they do the install, and the language is written that part of the maintenance agreement is that they will have remote internet access to the devices to do remote maintenance and diagnostics. And that's how they're writing their contracts today. These were considered turnkey systems. Turnkey should turn a light bulb on, as back then, as they put them in, the entire setup was from one manufacturer. There was no interoperability or very little across vendors. And if you go back and do a Google search and start looking at companies that were around in this space in the 60s, 70s, and 80s, there were numerous. But as we start moving into the 90s and internet technologies or IP networking, local area networking starts to get introduced, a lot of the smaller companies fell to the wayside because they couldn't make their products interoperable with other vendors that were adding all the new bells and whistles and make them available to inter-network. So they either got consumed and went out of business. All the communication protocols were largely proprietary. I worked on a project with, again, several students and some private sector partners. And we said, you know what? Let's go out and find out how many protocols there are that we can find across the globe. And let's reverse engineer the most that we can. And we found about 400, the catalog, we stopped at about 467 protocols. And almost over 95% of those were proprietary. All right. Fast forward, we go to second and third generation. Looking at second generation from the 80s to the 90s, we start to see distributed processing across multiple stations on the local area network. The size and cost of each station start to get cheaper. Why? Because before, they were all run by electromechanical relays. All right. Now we go to solid state devices. So we could reduce the size and cost. And oh, by the way, they generate less heat, consume less power. We can replace big boxes with server blades to do the same thing. And basically one of my takeaways, if we could put 10 bits in a 5-pound bag, right? So 10 pounds of bits in a 5-pound bag, because you have local area networking. Local area networking is bi-directional, correct? In those first generation systems, they use twisted pair wire, and for full duplex communications, two-way communications, you needed 2 copper wires going that way to the device and 2 copper wires coming back. So the cost of growing that network was expensive because you had to lay more wire. Whereas in networking, you can add another IP address, a little bit of LAN cable or some wireless. You can continue to add devices and sensors. So that's where we start to see the costs start to go down. And asset owners are not dumb. They want stuff, and the employees get cheaper. It's cheaper to hire a system administrator that can do networking than it is one of the operators that knew a proprietary language from a vendor that was not publicly available and not taught in any school anywhere. right? The only person that taught the engineering and design for those systems was actually the company that had their internal training, and that's how they dominated the market. So we had limited remote programming. You still need to call 1-800 my stuff don't work from the vendor if you needed a reconfiguration. True story. Marine stationed in Keflavik, Iceland, at the Naval Air Station. That was called Air Operations Center up there, and I was the security guard. And the only reason I had to work indoors at the Air Operations Center is because most of the posts for Marines were outdoors. Iceland, cold, snow, and most of the times we couldn't walk to check the bunker doors outdoors where they kept the bombs and whatnot. We had to ski. I asked the commander, can we get some, you know, what are those, not jet skis, but the things that run on the snow? Yeah, those things, right? I said, can we get a couple of those for the guys? So, cause one of the, ammo bunkers, it was 1.2 miles from one end to the other, and we had to go on skis. And he goes, no, Marines are fail-safe. We always keep the manual labor. Cause he was afraid to run out of gas when you need to respond. So he thought that was a fail-safe method. But point of the story is they hired, so if you don't know, airfield lighting and control, right? That's actually considered a SCADA system for the Air Force, and something went bad with the stuff. And they had to call a guy in, cause the Air Force at this particular point in time, I'm assuming the Air Force, cause the guys that were working on the watch were Air Force, but it was a Naval Air Station, so it could have been Navy. But he was colorblind, and the alerts he was seeing on the screen, apparently in Iceland, I learned what black ice was. I didn't know what that was before. But black ice and planes landing is not a good combination, right? Especially when they're fast movers. So they had these sensors on the ground, and an alert would go off on the guy's computer monitor to let him know that the temperature is getting to a point where black ice might have to form, and they send out the truck to spray pickle juice. I think a Navy guy was messing with me, but it smelled like pickle juice to me. But they would go out and get this truck that would go out and spray this liquid on the ground. It smelled like pickle juice, and it would keep black ice from forming. So sometimes we used to mess with the guy that was a control operator, and I never got this because he was blind. I'm getting to a point here. He was colorblind, not blind, but colorblind. So when the alert went off, he couldn't see the color. The thing was telling him, hey, you need to call out the pickle juice truck. So we knew he was colorblind, so we tell him, hey, get on the phone, man. Your light is blinking. Call the guy with the pickle juice truck. And they go out there and spray the truck, and they'd be pissed off because we interrupt their pizza break, or they were playing cards indoors and stuff like that. But the Air Force paid, called the 1-800 my stuff don't work, and call somebody to come out there, to go in there and come out. And I watched the guy because I had to escort him in there. And he went into the control panels for Windows 3.11 and changed the color, and literally did trial and error. He caused the alert to go off, and asked the guy, can you see that one? No, can't see that color. Try another. Okay, can you see that one? And he went through the color palette until he found a color. Yeah, that's a shade of gray that I can see. So that one's good to go. And I was like, how much did it cost for this guy to come? So I had to sign off on the documentation. It was $83,000 for this guy to fly out there, stay for 3 days, troubleshoot and change the color palette on this SCADA system, right? Just so this guy could to do his job. If it was the Marine Corps, we would have just told this guy, hey, you know what? We're really looking out for you. We want to match up people with their skills. There's a mop over there with a bucket with 4 wheels, so you don't got to carry it. And it don't matter if you can see what color the floor is, just mop. All right, just keep going. Start on one end of the room, work your way to the other. So, but a lot of these SCADA systems that we'll talk about, I'll come up with some similar examples that you can see. What's interesting here is we have this thing called smart RTUs. So initially, first generation, the SCADA systems work master-slave, and the slave is the device that's monitoring the sensor, like an actuator, or like the sensor that was monitoring the weather on the ground, or like your HVAC in your home. And then they said, oh, we're going to make them smart RTUs. And they weren't really smart because all they did was go from serial communications. They put a daughter board on there so they could do local area networking with it. And that made it a smart remote terminal unit. But it's not. It was still kind of a dumb piece of device. All it does is it does time division multiplexing and talks to the sensor device. It could be a flow meter. Right on a pipeline, how many gallons or liter are flowing by a particular point at any given time, or a differential pressure transmitter, right? It uses pressure to figure out how much fluid is in a tank or something like that. That's how these things work. And then we start to see IEDs emerge, right? And these are not improvised explosive device like the military would think. These are called intelligent electronic devices. And most of the young people are pose the question, you know what an IED is? I could tell you what, it's not. It's not an 8-track tape. All right, and a lot of them, oh, it's a smartwatch. That's an intelligent electronic device. No, but we're talking about SCADA here. So an intelligent electronic device is a endpoint device that's programmable, has memory, has some kind of CPU function, and can execute instructions on its own. And most of you have seen or touched one and don't even realize it. How many have a programmable thermostat in their home or their parents' home or something like that? That is an intelligent electronic device. And in fact, your HVAC is a SCADA system, right? Supervisory control and data acquisition system, or a form of industrial control system. And this is why. You can program it, you can go on vacation for 6 months and come back. Unless there was a mechanical failure or the power was removed, that thing would be operating exactly like when you left it. And this is one of the reasons why it's hard to do security on SCADA. I'm going to leave that as a punchline because I'll come back to it later. So third generation SCADA systems, right? We're moving right along. I'm just orienting you here. And from the 1990s forward, they start to use open system architecture, open standards and protocols. Some of you might have heard of DNP3, Distributed Network Protocol 3.0. That's an open standard for the electric sector. We start to see distributing communications across wide area networks. So when the power industry went to this thing, hey, we're going to reduce the power of electricity to the customer by allowing them to compete and set the prices for electricity like the stock market. In order for them to do that, they had to break government regulation and open up distributed wide area networking. This is why at one point I could live in Ohio and I bought my energy, my actual electricity, from a company in Philadelphia who sold it to me cheaper. I started getting all kind of advertisements in the mail. It was like the 0 APR credit cards. You get this for, hey, we'll give you a fixed 8 cents a kilowatt hour for the next 12 introductory offer for the next 12 months, and then I'll go to the regular market rate. I said, all right, sign me up for that. You're cheaper than Ohio. And on the 11th month, I start getting mailings from other competitors. And then I would switch to that other one, and they would call me, oh, why did you leave us? We love you. I said, because you can't continue to give me 8 cents per kilowatt hour. You're going to go up to about 15 cents. And this other company in Pittsburgh is offering me, 8.2 cents a kilowatt hour for the next 18 months. So I just kept switching while I was there. And that was a good thing for me, for the customers, right, for the consumers. But it also made distributed communications for wide area networking to interconnect these systems an issue because they open up the attack surface. We start to see the interoperable with third-party peripheral devices. So third-generation SCADA systems, remember all the small companies got absorbed or went out of business? Now the companies are developing devices that are backward compatible and interoperable with other vendors. And when you try to get their systems connected with you, and you say, hey, what's your turnkey system? I said, well, I don't need a turnkey system. I'm already up and running. I just need something that could work with Siemens, Omicron, and whatever other manufacturers that have. I said, yeah, we can work. You set our device, you get the default settings. All right, so that's like buying a car with no power windows, no power lock, no autopilot, right? And so, but if you buy all our stuff and get a turnkey system, we give you the power windows, the power locks, the power brakes, the free Wi-Fi, right? So, and that's what they're doing now. That is a selling feature. If you buy from one manufacturer, you get to turn on all the additional features to add industrial Internet of Things and additional sensoring and more flexible protocols. And the thing that broke the camel's back really is that reach back to enterprise networks. All right. And this is when the physical process system, the endpoint, started to be connected to the IT enterprise business network, to allow to be improved flexibility, reduce costs, energy on demand, things of that nature. I'll give you an example. How many of you receive a utility bill now by email or traditional mail in the mailbox, and somewhere on the front page, usually in the right-hand corner, or it's just right in the front somewhere, as soon as you open it up, before you see the price, first thing you see is a bar chart, or maybe a circle chart. Say, hey, in January, your kilowatt per hour was this much. And in February, it was this much. In this month, it was this much. And for me, in December, it was a real tall bar. It was like 4 times higher than the prior couple of months. And I'm like telling the wife, what the heck? What's going on? And problem was, we had a bunch of people come in. It was colder. Furnace was on all the time because we had people. And, you know, you kind of equate. Bigger bar, top box on the right is going to have a bigger price in it. And so I don't know what a kilowatt hour looks like, but this thing is getting damn expensive. So in order for that magic to happen, to show on the bill, to make the electricity sector more, instead of push technology, pull technology, right? We get the customer involved. Now you're going to react and start to do things to try and make those bars small every month and as even as possible. Because believe it or not, in the power sector, electricity sector, a lot of variation, it gets very expensive for them to provide you electricity. If they can get steady state, it makes it easier because they can predict the amount of power they need and keep the cost down. It's real difficult to balance that out for them. So what did I do? The next day, I ran down to Home Depot. There I got in the mail, I got a coupon to go buy a dozen curly light bulbs. It says round the box, glows like 70 watts, but only consumes 10 watts. That's gotta mean smaller bars on that bill next month. Right? So I went around changing all the incandescent light bulbs, and about 3 days later, my wife was freaking, "Hon, I'm downstairs making a coffee." And when she uses that voice, I know I did something wrong. So on my way up, I'm sorry, I didn't mean it. Whatever I did, take my car today. I says, that's a good idea on the light bill thing and changing the current light bulbs, but it sucks for me. I come in the bathroom, I turn the lights on, and it takes a minute for them to warm up to get bright enough so I can see to do my makeup. And I go, what's the problem? You got time management issues. Flip the switch, go dookie, and then come back when it's bright, You don't need to see when you sit on the toilet, Get it right. No, that was my third wife ago. No, I was just saying. But anyway, when we get to third generation SCADA systems, because they're using local area networking, TCP IP, we start to see some of the security issues start to proliferate. All right. These companies and asset owners can no longer contain the issues. And, we start to see from 2010 on, a quick ramp up of this. Now here you got a picture of what a SCADA network might look like. I'll step back a little here so I can use my pointer. I hope this thing doesn't go out on me again. But as you can see at the top right-hand corner, you got the internet out there, or the other power industry providers. And then in the dotted box, that is the business IT enterprise network, the ones that generate your e-billing. It needs to talk to the backside SCADA network, the data historian, to gather the information for your electricity user and your building and your apartment number, so on and so forth. Push it forward, and they associate it with your email address, your account, your check routing number, so they can, automatically take the payment out, so on and so forth. So the backside here, everything you see is what the SCADA network might look like. Now, I'll point one thing out. In first and second generation SCADA system, there's number 1 and 2. And oh, by the way, 1 through 5, these components you see, those are the key arteries on a SCADA network. No matter how big or complicated they are, they will have a master terminal unit or engineering workstation, human machine interface, a remote terminal unit, or a programmable logic controller. Remote terminal units are kind of analog. And then the cousin to that for third generation systems or generation 2.5 forward is a programmable logic controller, the communication links, and then the field devices down at the bottom. The further you go down this list, the softer the target is. The less stable or less capability it has to resist any type of cyber intrusion or probe that you have on it. Okay, and these symbols down here, this is the holy grail. So if I can get past this RTU, this node choke point 3, if I can get down here, anything I do below that will have a physical effect on the process, whether it be power systems, whether it be manufacturing, whether it be chemical processing, whether it be airfield lighting and control. You can mask anything you do down here from the operator. The only way you'll know something is wrong here is because you're physically observing something going wrong. Okay, just like they did in Stuxnet. Like, are those centrifuges supposed to be wobbling like that? You know, that doesn't look right. And so that was kind of, you see the observed effect. By that time, it's too late. All right, it's too late to do anything. So just wanted to give you an idea. And for first and second generation SCADA systems, there's 1 and 2 were physically in separate boxes. Those 2 devices were physical separate devices. When you get to generation 3 type SCADA systems, those are now in 1 box. So think on a workstation, a server, or a laptop. Both of those things are just applications, software applications you pull up, and they're logically on 1 box instead of divided by 2. Now this is the SCADA operator's view of what that looks like. So if you're an IT guy, everything here makes sense except those symbols on the bottom, right? Except these. Those are like, 7th grade science project type symbols. Those are actual, electrical engineering symbols that the operational technology folks, SCADA operators, use to identify their endpoint devices. This is how their community views it. They have everything in these, what we call the Purdue reference model. Notice that I have down here level 0 and level 1. It's a blind spot. This is the actual endpoint. But most of what operates down here at this level is not IP. Over 95% or maybe a little more of any connectivity that happens down here is non-IP. It's 4 to 20 milliamp loop currents or signaling in that manner. It works well, it's highly reliable, and it's immune to electromagnetic interference in these very noisy environments that they deploy these in. And they've worked that way for many, many years, and they still do. And you might want to ask, well, how come IP to the endpoint doesn't work well in this community? And the folks that came up with that idea was a great idea. It will work very well. But the problem that they didn't realize is that the folks that instrumentation technicians, system integrators, and asset owner operators have been doing this job for a long time. And if you go IP to the endpoint, they lose their job because they don't know how to do system administration and TCP IP. And so the unions fought hard to make sure that the asset owners do not switch to IP to the endpoint. Those folks are going to lose their job. That's just the reality. This is what I'm hearing from the community. All right, so let me give you a video here. I'll get a preface because right now some of you are wondering what might a SCADA attack look like. And so this was one attacking an energy management control system. It's in another language, so I'll kind of narrate, but it will be real simple to figure out. And he targets a programmable logic controller, all right, a PLC over a cell phone network. I'll get back here and we'll run this. Come. So he's giving the little preview. I'm going to do a hack here and I'm going to use my iPhone, and he's targeting that company from that building, and he's got his Hemeldunker, which is the equivalent of a flux capacitor. All right, so he's got his iPhone, and there's an app for that, so he pulls it up. It runs an automatic script because he gets an auto log on to the programmable logic controller, and he gets the equivalent of command prompt, and now he just executes legitimate commands, right? So he issues the command, and if you look in the background, it's like Karate Kid. Wax on, wax off. If you can turn it off, you can turn them on. And because these devices, again, for cost savings, you can connect multiple systems in close proximity for control. You jump over to another port, and you just turn it, execute a legitimate command. There's no logon, there's no username, password. Most of them still operate like that today, I promise you. I'm not making that up. So he did that with permission. Question?
So he was using an iPhone. Did he find an open wireless access point? Did he find an open a phone number that gave him access to the DL?
All right, so the question is, how did he actually route in that way? Well, for one, he did this with permission as a demonstration. And number two, they have a dial-up access point as a robust backup if the internet went down. So he was just simply calling the number to get remote access. In this case, you don't have to be wired these days, right? But he could have did it from a regular POTS line. Does that answer your question? So the particular company still uses a dial-up access because, in their eyes, they wanted a robust remote capability. They could have prevented that by doing what? Anybody knows what? Besides not having, what's that? No password. The system is not capable of doing that. You put a dial-back modem. Right? Everybody heard of that? Right? So that's one way to prevent it. You can call, and that thing has a set of pre-designated phone numbers that it will call back if you try to dial into them. And that's one way to kind of control just anybody from dialing up the number and executing commands. So but good question. A good question. So I started to look and say, this is more like a race to the bottom, right? So what can I do to a programmable logic controller? Because at the end of the day, it's just an ugly looking computer that doesn't look like a computer. It has CPU, it runs code, it needs a software application to interpret instructions, and a firmware is nothing more than a fancy word for operating system. So I started to look and say, wow, wouldn't it be neat if a company puts out a new firmware, right? Version whatever. Let's go with version 20. Version 20 is going to cover up and fix all the vulnerabilities and bugs that we had with version 10. All right. Let's just say that's the new thing. And so they send out an email to all their asset owners. Hey, come onto our website and download the latest version of firmware and update it, and fix all these problems we've been having, we've been fixing, and so on and so forth. And there's, rootkit problem and so what, and so forth, right? So what we did, I said, wait, is it possible for them to go to the website and pull version 10, thinking it's version 20, upload it, we tell them it's version 20, but it's really version 10, and then we can exploit the holes that were the vulnerabilities that existed in the first place, and the asset owner would know no difference. So we in fact did that. And so I'll go quickly here to satisfy the palate of some of the folks that are more technically focused. Basically, we located in the firmware code the sections that were related to the version number. We modified the version number, and then we attempted to recalculate the checksum. Because on upload, that's one of the things that the PLC is going to do to understand that it was loaded correctly. So we exploited a control logics. This is a Siemens. Not a Siemens, Allen Bradley device, L61, SLIC 500, for those of you that know what that is for the CPU. And these are actual screenshots we had. So here we got the loading process going on, and it says, hey, the current version is 20.13, and the new version is 20.66, and then at the end of the process, it says, hey, congratulations, you have now got the newest version. And in fact, we loaded even an older version that was on the device to begin with that had backdoor vulnerabilities that we can exploit. So we wanted to see if this proof of concept could work, and we did that. So this was actual demonstration of how we did that. Now, this was not trivial. It took some time. It took three people working, several weeks to figure out how to do this. One of the ways we did it, we use VinDiff for static and dynamic. We use a stepwise regression, going back through the code. We were looking for function tables and function blocks to figure out what they do. For that, we did bin walk. We also use IDAPRO. Anybody use IDAPRO? All right, we use IDAPRO to figure out, hey, it was using ARM, Little Indian. Right? And we figured that out, and then we determined the base address that it uses and figure out how the function blocks code and what checksum it used. So if you see the two lines on the bottom, when we started, it can only identify about 62% of the code when it was disassembled with IDAPRO. And after we figured out what function blocks did what and took a guess on some of them, we can see afterwards that we were able to identify about 87%, and that's significant in this world. And it was significant enough for us to be able to do what we did. So now we get to the part of the presentation where I start talking about what some of the challenges that we're facing. So a strategic approach to security, you got to understand. Most of the SCADA devices, even the third generation devices, are master-slave relationship. I didn't come up with that term. That's something they made up in SCADA. They work on a master-slave. But here's the catch. Most endpoint devices are designed to be loyal to two masters. On purpose, they design it that way. So you can have a handheld communicator or another master station by default talk to it, change some parameters on it, and guess what? It doesn't even tell you it cheated on you. It will not tell you I was talking to another master and they told me to change this, right? Change my upper range limit, lower range limit, or change my damping value. Anybody know what damping value is? That's a neat attack that I've done. All right, you know what that is, right? So you change the damping value, delay it by a second. That causes a system to get into what we call in computer science a race condition. It never gets to steady state because you delay the time. It says it needs to see this many changes before it reacts, and it just stays like this the whole time. It'll never get to a steady state. So that creates havoc. Know that their architectures are rather flat. They have point-to-point, multi-point, and submaster. That is not any kind of network topology that most IT people would know, except maybe point-to-point. Right, that's probably the only one that's familiar. So, for an example, you can have one of the reasons why it's hard to do network discovery or figure out a SCADA network without doing it kind of manually and probing on devices is you can have a PLC that's talking to multiple 15 devices, and then it's also talking to another PLC and aggregating the information that that PLC is collecting from other devices. So you get into this master sub-master role, and it flips amongst what it's doing. It's a sub half the time, a master the other half, and they're really hard to figure out and see that with kind of network discovery tool. So very little communications at level 0, level 1. Below the PLC and RTU are IP. There's a lot of analog signals going on down there. Again, the 4 to 20 milliamp loop current is the most popular. Here's another thing. SCADA systems, or let's say you have an issue, a cyber intrusion on the IT network. If it's an advanced persistence threat or very pervasive, what will IT people do? Bring down the service, rebuild the server, whatever the case may be, then bring it back online. In SCADA systems, you can't stop the process. You got to work through it. So there's 4 operational states that they work through. That's the completely automatic state. And oh, by the way, if you look at the y-axis, that is what asset owners prefer, because it's the most cost effective. It costs them the least. We start to go across that and do semi-automatic or manual operation. that's human intensive. And they usually don't have sufficient staff to be able to do that for long periods of time, so it gets very costly. And then the worst is an unintended stoppage, because some of them do stoppages on purpose to do reliability-centered maintenance and things like that, but they want to do it on their schedule. Right? They don't want you to get their systems to stop when they didn't expect it to, because that gets extremely costly. So I just point that out. All right, that with SCADA systems, they have sometimes a graceful degradation, most times they don't. And if there's a cyber intrusion of some kind or some kind of mechanical issue, you got to actually work through it. Think goal consequence-based security. The adversary is looking to do one of these top 4 things: either create a loss of view, manipulation of view, loss of control, or denial of control. There's multiple ways that they can get there. For example, at one place, we went and replicated an Apogee Siemens system and then deployed it for a large exercise. And this was what we did. This was the true condition on the left. I had to, what do you call that? Eradicate, or what is it? Yeah, whatever, man. I had to block out the names of the innocent, right? I can't tell you what agency or organization that was in this venue. But here on the left was the true state of the system, and the stuff on the right was what they were seeing. So it was telling them the temperature in the room and the server deck was a 70 when it was really getting real hot. And so what they ended up having to do was start shutting down services so they can get the room cooled off, and had to reprioritize their work, and that created a very expensive havoc for them. And I kind of threw a wrench in their gears for their global operations for transportation and logistics. It really threw things off because they had to reprioritize their services until they could get things cooled down. And it took them like 6 hours just to figure out what was really wrong, because I didn't make the AC units inside the server decks go bad. What I did was I made the heaters on all the surrounding rooms go up. All right, and then I didn't let the AC units in the server deck go on to cool them off. I just told them, hey, the temperature's normal. So they kept coming on, coming off, coming on, but they never cooled the room enough. So I incrementally increased the heat in the room by making all the other rooms around it hot. They were empty, storage rooms. Nobody works in there, so they didn't detect that. All right, so operational system, OT system attributes are, again, host endpoint can operate without network service. Think of your HVAC system. You could program it and leave and come back 6 months later and it's still working, unless something, mechanically went wrong or you lost power. They're designed this way for reliability. These systems have highly deterministic behaviors. You don't see a lot of applications coming up in the morning during the workflow day, and then at night everything goes down. These systems are designed to have a sensor, talk to a programmable logic controller, and it gets asked the same question over and over again. What's your temperature now? What's your temperature now? What's your set point now? And it does that over and over and over. So deterministic behavior is the norm. All right. And it's real easy to do that. This makes whitelisting a very highly effective approach, because these systems don't execute a bunch of different actions based on the user and the endpoint. The endpoint is actual physical process that is monitoring. The opcode instruction sets on the firmware are typically very small, and there's little forensic capability on any of the devices, if at all. They're trying to do that now, but because the overhead that it requires, because these are real-time operating systems, they usually can't deal with that additional overhead to have an audit capability or encryption or anything like that. Everyone's a super user in this community. There is no separation of privileges, regular user from a super user. Everybody has domain admin rights to log on to these things, and that's a safety feature. The system usually doesn't alert you to any parameter changes that are made. That's a configuration issue, that we got to deal with. That's how they're made. And a lot of these are, I'm jumping the list here, a lot of them are flat networks and they're pervasive that way, but it's hard to look into them. So it's more art than science at this point to enumerate these networks and figure out what they're doing. And so that in turn favors the bad guy right now, because there's nothing in there that gives you alert unless they trip over something very loudly or make something stop working to give you any indication that they're in there. So what about safety? So we're security professionals, and we know that everything IT security can be mapped to confidentiality, integrity, and availability for the most part. But I will tell you, in this community, safety has been around for much longer. They know how to measure it, and if they don't comply with it, they get fined. All right, to them, cybersecurity is nothing more than an expensive smoke alarm that will tell me that something is wrong, but it still can't do anything. All right, it can't prevent anything from happening. That's kind of the view that they have. So I want you to recognize that in the SCADA community, security is a competing objective with safety. And the way they view it, the more security they have to apply, the lower their safety threshold. Whether that's actually true or that's how they're visualizing it is an issue. So you need to introduce security to them in a way that complements their safety, all right, or improves their safety threshold. So a couple other things is that we see that the life cycles for these systems, when they put them in, they don't expect it to be replaced every 3 to 5 years with the newest thing. They have on average 12 to 15 year lifespan. Power industry, a lot of those hardware components are expected to last 20 to 25 years before they need to be replaced. Understand that that is their business model. So when you have IT security solutions coming from the IT side over to SCADA, all right, and then that technology keeps changing because IT changes, every 3 to 5 years. The security technology changes. You're trying to put a square peg in a round hole when you bring over those solutions to the SCADA arena, and it's largely because of this right here. So you see these priorities in the IT world: integrity and confidentiality. Solutions for security are usually the first two priorities. When you come over to the industrial control systems, they could care less about confidentiality. They care more about availability. So there's a competing issue there, all right, with that. And the last thing I'll leave you with here is I'm going to show you one more video. And this one here talks about the two communities, the IT and the OT community, and how they view the security problem. So this just goes to show how two groups of people can agree that they have a problem with security, but cannot come to agreement on how to solve that problem. So looking at it through different lenses.
You're 75% to you, Palma.
Can you hear this?
25% divided between the five of us.
Yeah. What's that?
Crowbar, myself, Tom, and the baby. That makes 5% for each one of us.
Hey, close the door. We gotta close the door. I was just coming in.
All right. Get out, man.
Listen, Tom. I wouldn't.
All right, so you'll see what they write on the board here. So the guy in the suit is the IT security guy. He's trying to tell them, look, this is how security works. And Ma and Pa there is like, no, it doesn't quite work that way. So he's doing 5 into 25. She's like, no, those firewall rules are not going to work on my system.
Into 25. 5 won't go into 2.
No.
But 5 goes into 5 once. Now, we didn't use the 2 before, so we're putting it down here. Now, 5 into 20 goes 4 times. There you are.
That's SCADA Security 101. Everybody knows that. Hold on. We just got another minute here before we be done.
5 times 5 is 25.
So now they're bringing the CFO. This is...
14 is 25. 5 times 4 is 20. 5 times 1 is 5. 20 is 5.
Drop the mic. All right, we're going to try this one more time. This got to work. It has to work, guys.
5 14s is not 25. 4, 8, 12, 16, 20, 21, 22.
All right, I show this video. It's kind of funny, but I've been in rooms with groups of people trying to decide on how to mitigate, these security problems, and that's what the conversation looks like at the end of the day. Well, thanks for coming. I appreciate having you. You guys have a good day.